Hello and welcome to the Chapter 6 podcast on Section 6.7. Today we're going to be talking about many electron atoms or elements that have more than one atom, so beyond the Bohr model. So what we find is that electron structure initially is very similar to hydrogen, but as we add more and more um, levels, things begin to get a little bit more complicated, but not in a non-logical way, hopefully. Because there are multiple electrons, the energies of the orbitals will change, and we can see that that there's some overlap between some of these quantum levels. So if you look up here, the figure on the right, notice how 4s begins before we actually finish filling in 3d, and you notice each box represents an orbital. So remember, s's were sphere orbitals, so there's only one orbital, one box to fill. Whereas remember when we talked about p orbitals, there were three p's, so that's why there's three boxes to fill, because there's three p orbitals, one in each orientation. And for d, remember there were five. But notice that that there's this compartmentalization, and notice how there is overlap between these levels, especially as you get further and further away. And notice the differences between these 3D and 4S and some of these other ones. They start to get very, very close as you go further away. Kind of similar to what we saw with the atomic emission data way back when we were looking at hydrogen earlier in the chapter. For electrons, we do have to consider repulsions, because as you add more and more electrons, there's more and more repulsive properties. So they have to be arranged in a way that minimizes repulsions and maximizes attraction to the nucleus. When we have many electron atoms, the energy of the orbital increases with the value of L. And we'll talk more about how this diagram you see here with the boxes relates to some of the quantum numbers we did a couple sections ago. And things that are degenerate orbitals with the same energy. So, for instance, in the P's and the D's and the F's that aren't on this graph, those would be considered degenerate because there's multiple orbitals and they all basically have the same energy. Spin is also something we have to consider. Spin is basically, the way the electron is rotating as it's moving in its wave-like property. And what they find is that spectral lines that we saw were closely spaced pairs for multi-electron atoms, and that doesn't mean a whole lot right now, but later on it will. And what we find is that electron spin is also quantized as well, so it carries energy, which makes sense because we talked earlier in thermodynamics how the bond energy is the potential energy of our chemicals. There are also quantum numbers to take into account spin, which is either a plus 1/2 or a minus 1/2, and this represents the direction of the spin. We have some that spin counterclockwise and others that spin clockwise. And this corresponds to some other things that we'll talk about as well. And because of this spin and because electrons have a charge, it does produce a magnetic field. To help us with these different orientations and these multi-electron sublevels, we have a principle that kind of helps us place electrons in orbitals to ensure that that stability is being considered. So, for instance, we have the Pauli exclusion principle. The principle directly states that no two electrons within an atom can have the same set of four quantum numbers n, l, m sub l, and m sub s. So in other words, if you have all of these numbers for an electron, only one electron can have all four of these numbers simultaneously. Now, if we only have one or two of these numbers, that could apply to many potential different electrons. But if you have all four numbers, then that's one electron and one electron only. An orbital can hold a maximum of 2 electrons, okay? And they must have equal and opposite spins. So if you think about the magnetic field thing, if you have one generating a field in one direction, spinning in one direction, and you have another one spinning in a field of an opposite charge, they can kind of counter each other and exist within the orbital without repulsing. And so the way we represent this with quantum numbers is that they'll have the same n, l, and m sub l, but their m sub s will be different. One would have a plus 1/2, the other one would have a negative 1/2. We represent this in arrow diagrams for electron configurations, which we'll talk more about later, by representing electrons in an up and down arrow, which is meant to represent their equal and opposite spins as well as their opposite fields of magnetism. And that is it for now.